To start off this video with talking about physics, and I do a lot of different experiments on this channel, and I make a lot of assumptions with my experiments, but I prove out my assumptions experimentally, and that's kind of my thought process, right? I think that's how you move science forward, is that you make assumptions, but then you prove your assumptions, and then if you can prove repeatedly that your assumptions are accurate, then that changes the game, right? That means that we need to investigate further and create theories and develop science further based off of that. That's like science. That's how it works, right? And then so within that, I don't know if a lot of people know this, but there's really like two camps when it comes to physics and like how the universe works overall. Like when we're like zooming out the lens as far out as we can, you essentially have two camps and really overall. It's either that the universe is discrete, meaning that like relativistic physics rules everything around us. There's like particle physics is like the supreme and all of that, and like there's different. Everything is different and discrete. So like physics is different than chemistry, which is different than biology, which would be a different process than evolution, which would be a different process overall than mathematics, etc. Right? And then there's the opposing viewpoint, which is, for lack of better terms, that the world is digital as opposed to discrete. And digital isn't like the pure right word. I just like that's the word that I can think of within English to put around like the opposing viewpoint to discrete. And then so within that, one of the most common viewpoints within that would be Wolfram's computational theory, right? And then so personally, everything that I do on this channel and pretty much all of my physics experiments, I'm in support of Wolfram's computational theory, flat out. Like if you can disprove Wolfram in these areas, then you can disprove me. But essentially, overall, what my large hypothesis is that these processes are not discrete, that they there's so much overlap to them that they're all essentially the same thing, that like biology operates essentially the same way that chemistry does, which operates essentially on the same levels that physics does. And then so within that, we should be able to take concepts like a neural network, and then it would be able to work across multiple forms, right? And that's exactly what I'm going to showcase to you within this video. So I'm going to showcase swarm algorithms specifically as the base, but I'm going to utilize swarm algorithms as a diffusion network to recreate an image. I'll use it for, and then also for NLP processing, and then I'll shape the swarm algorithm itself into a swarm neural network. And then I've already open sourced this fully. Swarm neural networks are something that anyone can utilize. They're MIT licensed. I'm the creator. And then so essentially, this notebook explores the application of swarm intelligence in neural networks for both image generation and natural language processing, or NLP. It introduces swarm neural networks that utilize agent-based optimization techniques to reconstruct images and text by iteratively refining their states. And then just showcasing, like I've developed this method maybe like a year ago. It's been on Hugging Face for a year or so, but like they change and they update their spaces all the time. And it's been a while since I haven't showcased this on my channel. So here we go. So within this notebook, the key components of this notebook are that swarm-based image generation. A swarm neural network is designed to optimize an image towards a target image using 1,000 swarm agents. Each agent maintains a position representing an image and a velocity, refining itself over multiple iterations. The optimization is guided by noise reduction strategy, where agents iteratively move closer to their target image. The mobile VNet-2 deep learning model is used for feature extraction, and the generated image is displayed at regular intervals, and the mean squared error between the generated and target images is logged. Let me just show you this. And so diving into this very specifically, to me, overall, there's, again, a huge overlap. I put Wolfram's computational theory at the forefront of this. And then so when it comes to these things, especially within diffusion, people often think of diffusion in terms of temperature and in that space, right? That's where temperature, or that's where diffusion, as a large process, is mostly involved in physics. But diffusion is involved in other areas of physics, for example, fluid dynamics. And then a lot of these processes within AI are actually fluid dynamics processes as well. And then so that's essentially what I do within this. So I take a image and a sample and a target image, this cat image here, and I upload the image. And then I train a neural network, these swarm neural networks, so these swarm agents, to essentially recreate this image, right? So they start off with a noised version of the image, and then they denoise this. So the cool thing about this, like the fascinating and amazing thing about this, like Epoch 50 here, what we're looking at, like this isn't a picture. This is swarm agents, like literal agents, like little, each agent is a pixel, and then they're making this image of the cat. Like, so like to me it's got a kind of a 3D effect, and then like compared to an actual photograph, and like this is literally different technology than an image, right? Like it's literally these agents are making the image. You can see here I have 1,000 agents, and then they're going through, and then I can adjust like the brightness, the contrast, and the color balance of the agents, right? And all of that, like I put that whole lecture at the top, right, as to like all of this is related in ways that people don't understand, because I wouldn't be able to do things like this if it weren't true, right? And that's kind of why I support and I look at these things overall. Like there's no way in this universe that I should be able to take swarm agents, turn them into a swarm neural network, and turn them into a diffusion process, take an image of a cat, and then take those agents, like 1,000 of those agents, and then all of a sudden they recreate the cat. Like I mean, this is literally agents, right? This isn't a picture. It's like, so this cat JPEG here is literally different than what we're looking at here as far as like the end epoch, right? So these two separate images, it's awesome, right? And you can tell like it's not 100% identical, right? Like the agents are not 100% aligning with the target image. They're off a little bit, but they're imitating the image. It's so cool to me, right? Like this is literally swarm agents doing this. And then so next step, right? Well, like, okay, can we utilize swarm agents for like actual like NLP type of tasks? And can we utilize, first of all, can we utilize diffusion for NLP tasks? Let's ask that question, right? And the answer is yes. Very simplistically, let's take a look at that, right? And this is a simplified process where essentially I'm replicating the diffusion process by injecting noise into like tokens in this model. So I'm taking a T5 model, like a transformer model, and then I'm like I can replicate diffusion and the whole process of diffusion itself within like transformers models themselves. The output isn't very good, and I haven't figured out how to like get this output to be like extremely good compared to like NLP and other processes, but you can do it, right? Like it's 100% translating it, and it's possible. There's just some lever here that I don't understand when it comes to diffusion and transformers and how they interact overall specifically, right? But then, so I can fix that by what we're doing here. And I was hoping that this is taking just forever. So I'll wait for this to go through, and then I'll try. Like, so I'll give you this trained model that I've been training as I've been going through this, which is essentially a swarm neural network that is fused with a Bert Base uncased model, and then it's going to be an NLP model, and it's going to create. I have a target text of the quick brown fox. I'm only going to train it for 3 epochs with 100 agents, and like it's going to get 100%. Like I already know it will before it trains this, but right now I have to pre-compute essentially the full entire Bert Base and encodings. So I need to encode just so I can get to the quick brown fox and do this experiment. But I want to properly train this model for you, which is what I'm doing this for. Like some people ask, like sometimes for me to like actually like release these models that I'm talking about on the channel. It's never that I don't want to release them. It's just like I don't ever usually fully train out the models, right? Like at this point I would just cut it off because I know it works. But I'll release the model for you after it's done training here as well, and then I'll leave a link, of course, to this Colab notebook. And then if you like this type of content, please like and subscribe. Thank you very much.